Welcome! This is Team 9, design of a practical model of a sustainable energy system for public demos. Our team members are Mark, Raihan, Judith, Deniz and Yeezy. The electrical system has changed notably in the past few years, in response to the ongoing worldwide agenda of sustainable development coupled with the public's augmenting environmental concerns. In particular, conventional sources of generation with fossil fuel-based plants are rapidly being replaced by sustainable sources as they cause far lesser carbon emission, hence addressing the issues related to global climate changes. In order to achieve a complete decarbonization like the Net Zero 2050 in the Paris Agreement involving EU countries, the world we live in today needs to be increasingly powered by renewables. In addition, the demand for electricity is forecasted to increase within the next coming years due to electric heating and electric vehicles, and this will put massive strain on our power system as it will struggle to balance these huge loads with uncertain and variable generation sources. Because of these challenges, change towards widespread renewable integration is not moving at the rate required to meet the targets. With this project, we want to raise awareness and inspire the public to find out more about renewable sources integration in order to show them that more effort is required to achieve the goals, but that there is hope if pressure is put on the government, research bodies and power companies. The aim of this project is to create the detailed design of a physical model coupled to a power system analysis software that can be used to show the impacts of renewable energy generation and new types of loads, such as heating and transport, on the electrical system. Our sustainable energy system model has three subsystems: the physical subsystem, the simulation subsystem, and the application subsystem, which is controlled via a tablet. A physical wind turbine model is made with 3D printing. The 3D printed wind turbine model can be driven by a fan in different speeds to simulate wind speed changes in the real world. It can also send the speed profile in real time to a computer by using an incremental magnetic encoder. The physical solar panel model, which the core part is composed of an LDR circuit, can detect the surrounding brightness and produce a corresponding current signal in order to simulate the operation of a solar panel in different lighting conditions. The simulation model is designed with the MATLAB-based block diagram environment called Simulink, which runs on an Arduino microcontroller board. This subsystem contains renewable and fossil fuel-based power sources. This sustainable energy control system is designed to emphasize heavily on running simulation work in order to observe impacts in a real power system. It can show different power system states with the input data from the public's interactions of the physical elements. In our simulation model, there are also models to enable future storage systems and faults which can be toggled on within the application to represent extra physical assets of the practical model. Our Power Network application on the tablet will provide real-time performance analysis on how efficiently and smoothly the public are running the power system with the current setup that they have chosen and decided to operate with. In order to assist the public, the application has direct instructions to avoid any confusion and to guide the user during their interactions with the model. Our real-time sustainable energy system for public demos was achieved as this system was successfully integrated into a working demonstration prototype where people can customize future energy sources distribution of our model by changing the parameters in the app interface. They can also blow wind on the wind turbine or shine light onto the solar panel to change the power generated from the sustainable sources. All data is processed with our simulation model in the background computer. Overall, the aims of this project has been achieved. The computer-built simulation model was successfully developed and tested. The microcontroller which was chosen to act as the interface between hardware and software was tested together with the app which was developed on a tablet. It was verified that both elements were successfully operating with real-time data transferring capabilities. The wind turbine and the solar panel representation had been successfully developed and necessary testing was done seamlessly.